of you here today. That's about half of you. I think we have 32 or 34 of you total. So today is a body in motion lab, and we are down, like I was just mentioning, to the last 6 classes. So this is our last regular lab in my Newton's lab section. But next week we are going to be building a little launching system, like a catapult, in our Thursday class. So a week from today, there will be some materials for you to gather if you would like to build a launching machine to play our Angry Birds game. So remember, if you recall that, here comes Nate, that we are going to have a force in motion or physics Olympics for the last Thursday of the last week of school. So that would be my last class with you guys. And my thought was that the Physics Olympics, participating in it, again, is optional, but it'll be extra credit points. So if you are looking for a way to boost your 4th quarter grade, since there isn't going to be an exam, however, by the way, there is going to be one test, one last test, and that is going to be on Newton's laws and speed and acceleration, so force and motion. And it's going to be on Friday, the 22nd. So that is not tomorrow, not next Friday, but the Friday after that. So it's in 2 weeks from tomorrow, is our one and only test in this unit, and that will be the end. And so then the Physics Olympics will have the Great Tankini. So if anybody's been practicing pulling a tablecloth out from under dishes, that is going to be one of our events. Pennies from Heaven, where the competition will be about who can get the most pennies in a glass by flicking the card. And then we also have, shoot, you can't do that one. Oh, our hula hoop challenge, which is going to be a Simon Says game with hula hoops. And so that will be fun. So having just one size hula hoop is all you need for that. And then our final event is going to be an Angry Birds game that we're going to play with our launching machines that we're going to make next Thursday. So I have posted those lab materials for you. I'll post them again, especially for that. I'm going to make a catapult out of mousetrap. And maybe you might want to make that too, and maybe you want to make something else. So there's a few options, and you can be creative. As a matter of fact, I think one of the categories is maybe we'll even judge the catapults on who is the most creative with their machine. So anyway, today, a body in motion, you're going to be investigating how speed affects where you must release an object in order to accurately hit a target. You're going to be able to explain in terms of Newton's laws of inertia. So really in all of Newton's laws, but specifically Newton's first law of inertia, is going to be as part of your explanation or conclusion for this lab. You're going to need to be able to relate what we're doing today to inertia. Okay, so things that are due. Well, we have 2 labs today. We had one on Tuesday with the hula hoops called Hula Hoopla, and that is due on Friday by 2 p.m. And then we have today's lab, which is a body in motion, and that is also due by Friday at 2. But let me tell you that the reason I have both of these due by Friday is because that's what Mr. Wolford would like us to do to keep it easy, that everything is due all at the same time. I personally think that you guys could probably use a few more days on this lab if you are not here right now today and you're looking at this later. So I have actually put the due date for today's lab to Monday at noon. To give you some extra time. I'm still telling you, it's still posted that it's like due by 2 p.m., but if you don't get it in by then, it will not show up as overdue until noon on Monday, and I will not mark you late. until after that point. Okay, so I did that just to give you a little extra time in case you needed it. So again, materials you need right now are some type of a target, hacky sack or bean bag, something like that, or a ball, some type of a measuring stick, like a yardstick or a meter stick, or tape, a ruler, or a tape measurer, anything like that will work. And that's all you need. Oh, and a couple of objects to use as markers, like rocks. All right, so this is, oops, this is somebody's, yeah, let me,
you can't say that that's obsessive.
sorry, somebody is unmuted and I'm here.
That's a little over what it should take 15 minutes at a problem.
Okay. All right, so well, let's go ahead and pull up.
It did take 15 minutes. Right.
Keep it right here.
15 minutes.
All right, so
that problem. How long would that
let me see. Somebody has their microphone on, and I am trying to see it. But
and you agree that 15 minutes to answer one problem.
You guys know it's apparent I'm hearing that I can't see that anybody has their microphone on. Okay, it stopped. Okay, thank you, whoever that was. You should have been muted already, but for some reason you're not. Okay, so here is our document. Let's see here. Get this out of the way, and you should be seeing our body in motion document right here. Okay, so, and I do, by the way, have my Dojo device handy. So if anybody is going to, I'm looking at all of you right now, raise your hand if you are participating today in the lab along with us. You've got your hacky sack and target and what have you. Anybody? Nobody? Now, I know a few of you have been doing so. I think that Derek and Trevor have been participating. Trevor, are you going to participate today? You going to do a body in motion with us?
Nah, I'm good.
You're good?
Yeah.
Okay, how about you, Derek? You gonna go do this along with us today? Okay, well, all right. Well, I was going to give dojo points for that, but no big deal. You guys can still get dojo points for participating in, Yogi just took off with my water glass. You guys can still get dojo points for participating by answering questions and yeah, volunteering some information as we go along. Okay, I see somebody wants to chat here. Okay. So Derek doesn't have a beanbag or a hacky sack. Derek, how about you can use like a ball? It will roll a little bit, but that's okay. Or, you know, another thing you could really use, I suppose you could use a rock. Really, you could use just about any object that's not going to break when you drop it. So yeah. Really, you can. So a rock would be okay too, and I bet you could find one of those. All right, so then Derek might be participating once he finds his rock, perhaps. Okay, so let's take a look at what the purpose of this whole thing is. The purpose is to apply the law of inertia in order to strike a target while you're in motion. So in this experiment, you're going to try to drop a hacky sack on a target as you run past the target. You think it's easy? Well, before you begin, try to guess what will happen as you increase your speed. So you're going to try to figure out when you're going to need to release the hacky sack in order to hit the target. And the first thing we're going to do is write our predictions down here. So then the letter A right here that says hypothesis. This is the first thing you want to write in your lab, on your lab sheet, is your prediction. So you'll see that there are 3 blanks below in that hypothesis statement. So you're going to fill in those 3 blanks. So I've got in parentheses here a couple of questions. These questions are rhetorical. In other words, think about these questions when you then fill in these blanks. Okay. And so if anybody would like to help with this, would anyone like to maybe read the hypothesis or what we're predicting, what's in the parentheses there for some dojo points? Anyone want to read? You can raise your hand if you do. I'm looking. No. Oh, Nate's going to do it. All right. Thanks, Nate. So you're reading what's in parentheses right there. What are we predicting?
All right. Let's see. Predict where or when you think you will need to drop the hacky sack to hit the target when you are moving. How accurate will you be? Would it be different if you were running?
Okay, great. Thank you. And there is Nate. Okay, so yeah, so you're predicting then how you're going to, or where I should say, you're going to drop your hacky sack or your rock or your beanbag or your peas or whatever you're dropping or your ball. You're going to predict where you're going to drop it in relation to the target while you're moving. And then how accurate will you be? You're going to do this at 3 different speeds. So you're going to walk first, and then you're going to like jog, and then you're going to run. So as you are speeding up, your prediction is where are you going to drop or release your item, your hacky sack, when you are moving. And the faster you're moving, are you going to have, how are you going to have to drop it differently? And how accurate do you think you'll be as your speed is increasing? So your blanks here, say, well, so your hypothesis, I'll read that, and then this is what you'll put in the blanks here. So if I'm in motion with the hacky sack, I will have to drop it blank the target in order to hit the target. Let's stop right there. So let's look at that first blank. So before we go to answer it, think about what is happening with the hacky sack when I am holding it. I don't know if you can see me. I think you can still see me in this corner. Okay, so when I am, what I can do is actually stop the share for a minute. So when I am holding this hacky sack right here, is the hacky sack moving? A couple people joining us here. So I'm going to ask you a few questions, and if you want to answer this, just go ahead and I'll let you unmute yourself. If you have the answer, unmute yourself and answer for me. Describe the motion of the hacky sack right now that's in my hand.
It's not moving.
It is not moving. That's right. And that came from Trevor. Okay, thanks, Trevor. I'll get you some dojo. So it's not moving right now. Now, what if while I'm holding it, I start running? Then, according to Newton's first law of motion, if the hacky sack isn't moving, what's going to make it move? According to Newton's, I guess, second law. Its first law says it's going to just stay at rest unless something happens. And that goes to our second law. So what has to happen to the hacky sack in order to make it not be at rest anymore?
A force.
A force. Okay. So if I am then running with the hacky sack, describe the motion of the hacky sack while I'm running with it.
You're putting more acceleration on it.
Okay, and it would be moving at the same speed as I'm moving, right? Because I'm holding on to it. And so if I'm speeding up, it's speeding up. If I'm slowing down, it's slowing down, because I have a hold of it, right? So it's with me. Now, when I drop it, I will no longer be that force that's making it move, and it will be out of my hands. Now, what's going to happen when I drop the hacky sack? Get my Dojo back out here. What's going to happen when I drop the hacky sack? Easy question. You all know this. Just literally. Oh, I got to turn my buzzer on. I just gave you Dojo, but you can't hear it. So is it going to float in the air when I drop it? What's going to happen to it, Andrew? What's going to happen to it, Nate?
It'll hop and it'll stay at rest.
It's going to stay at rest. No, wait. No. Is it? So if I drop it, it's just going to stay at rest? So it's just going to hang there?
When you drop it, it's just going to kind of move a bit, and then it's just going to stop and just sit on the ground.
So how's it going to move? What direction is it going to move?
By gravity.
Okay, so gravity is going to pull it down, right? So, well, it's with me. It's going in the same direction as I'm going and at the same speed as I'm going because I am the force pushing it there, right? When I release it, no longer is it with me anymore. So it doesn't just hang there and stop because there's still a force acting on it. So it's going to fall down to the ground, right? What is that force that acts on it? You said it. Somebody did.
Gravity.
Gravity, right. I think that was Sean.
No, I think it was Andrew.
Oh, was it Andrew? Okay. All right. Oh my gosh, my phone's blowing up. So it's like when I turn the phone on to have Dojo, I also am listening to all of the texts here. Okay, there you go, Andrew. All right, so it's pulling it down. So gravity is the unbalanced force that is making the hacky sack fall to the ground. It's accelerating towards the earth. Why? Because gravity is the unbalanced force that's moving it down towards the earth. It's going to stay in motion, though, for a little while. So backing up to our prediction is where are we going to, if we're going to be walking towards the target and then, increasing our speed, where do we need to release it in relation to the target? We're going to release it when we are past it, right directly over it, before we get to the target? What do you think?
You need to throw it before you get to the target.
So we're not going to throw it, by the way. We are going to just simply drop it. Okay, so we won't throw it. We're just going to release it. It's going to be in our hand, and we're just going to open our hand while we're running up towards the target. So what do you think? Where should we release it? Okay, well, nobody is responding. Okay. Oh, you guys are chatting it to me, aren't you? I have a feeling. Let me see. All right, I'm sharing this document with us so we can write things down. Okay. I was hoping you guys would say it instead of chatting it because I've got to get to my chat and it's all behind everything. All right. Let's see. So PJ is saying gravity will pull it down. Gravity, gravity. All right. Yes, gravity is the unbalanced force that will pull it down. Now, what does Newton's second law say? I've got the wrong document up. What does Newton's second law say about I'm sorry. What does Newton's second law say is going to happen to an object when an unbalanced force, like in this case gravity, acts on it? So hopefully you have your Newton's laws notes with you because I said you need them each day, and I meant to actually have that on your slide. Yes, Imagine.
So basically when another unbalanced force acts upon it, if it's a stronger balanced force, it'll make the other object move.
The object will what?
It'll make the stronger balanced force will make the other object move.
Okay, it'll make the object move. So what if it's already moving?
It'll make it move quicker.
Yes, it will make an object accelerate. So remember, Newton's second law is that relationship between force and acceleration. So if you have an unbalanced force acting on the object, not only will that object move, it will accelerate. So what does that mean? If it's at rest, it'll start moving, right? Isn't that still acceleration? Because remember, acceleration is a change in speed or direction.
Yeah.
Technically. So even if it was slowing down, but what I was trying to get you to say is that gravity is going to make it accelerate towards the ground. So it's going to move toward faster and faster towards the ground. Okay, going back to our hypothesis then. So if I'm in motion with the hacky sack, I will have to drop it blank the target. So before the target, after the target, or on top of the target. What do you think? John's got his hand up. What do you think, John?
You will have to drop it on the target.
So right when you get directly over it, that's when you're going to drop it?
Yes.
Okay. What if you were running now instead of just walking?
You drop it before.
Yes, I agree. So remember that according to Newton's first law, an object in motion wants to stay in motion until an unbalanced force acts on it. So it's going to stay in motion when I release it for a moment. And the faster I'm going, the faster it's going, right? So wouldn't it make sense that the faster you're moving, the earlier you would need to drop it in order for it to hit the target, right? Because it's going to keep on moving in that same direction and at that same speed until gravity pulls it down. So gravity will be acting on it. But do you think as soon as I release it, it's going to immediately go straight to the ground, straight line? So it might if I'm walking, more or less. But the faster I go, the more projectile motion it'll have, the more it will be like an arc. So you'll have to drop it earlier. Okay, so you'll want to fill that in. How I would fill this in if I was making the prediction, and this is your choice, but I would say that I will have to drop it before the target in order to hit the target. And the faster I move, the earlier I will have to drop it, and the probably less accurate I'll be. And I wanted you to think about the challenges that Air Force pilots might have before they invented the guided missiles that they use today. They had to do something like this. And I had a video pulled up for you on dropping bombs. I decided not to play it though, for a couple of reasons. Anyway, you could be thinking about that. Imagine, you know, if you were flying a plane and you had to drop something to hit a target, you would have to be dropping it way before you hit the target because you're flying at top speed. So your target, I mean your bomb or whatever it is that you're dropping would be moving in the same direction at the same speed as your jet for a time until gravity pulls it down to the earth. Okay, so we've made our prediction. We're going down here to our procedure. So we're going to place the target about 10 to 15 meters away from the starting line. And we are going to place an object, which I'm going to use a rock, along the path where we think that we should release the hacky sack in order for it to hit the target. And then we're going to hold the hacky sack in one hand and we're going to, you know, go towards the target. We also want to have a measuring stick of some sort or a measuring tool, because what we're going to be putting in our data table, if you go down to your data table, what you're going to be turning in for a grade is the information on this data table that we're going to do together. And then you're going to write a conclusion. So it's just a paragraph right here about how your speed affected when you had to drop your ball or hacky sack, whether your data supports your hypothesis, and how inertia applies to this. So this is going to be what you're going to do for homework. And if we've got enough time, we'll talk about it. I mean, we did just talk about it just now in our prediction. So what we're going to be doing here is we're going to be getting, sorry, we're not actually calculating speed. This is just we're going to be walking, jogging, and running, and we're going to be recording our distances here, and then whether or not we actually hit the target. Okay, so by the way, on your worksheet that I gave you, I did not have this did it land on the target part. I thought about it afterwards. So if you could maybe add this on yours, because how are we going to know if we were accurate? I mean, maybe you'll remember, but just make a little extra column here to say whether or not your hacky sack or ball or whatever landed on the target when you're walking, when you're jogging, and when you're running. Okay, so here we go. And I am going to try to set this up where you can see my target. And you guys are setting up your targets also. Ooh, it is getting really bright out here. Okay, so I think maybe you can't see it yet. It's so bright, I can't see. Can you see this target? I think. Oh my gosh, I can't see anything. All right, well, I'm gonna hope you can see the target. Asher, can you see the target, this paper right here? And my hacky sack's in the middle of it and Yogi's staring at it? Move, Yogi.
Yes.
You can? Awesome, thank you, because I can't see a thing, I'm blinded. All right, so hopefully you'll see me back here too. The first thing I'm gonna do is going to set my rock where I think, where our rocks where we think we're gonna need to release in order to hit the target when we're walking, jogging, and running. So I've got 3 rocks here. And I am going to place them. I hope you can see this. So what do you think about the, where should I release the earliest? Should it be when I am running, jogging, or walking? Where should I release the hacky sack the soonest?
When you're running.
Anyone?
When you're running.
Okay, when I'm running, yes. And then, so where should I drop it the closest to the target?
When you're walking.
When I'm walking. Okay, so I'm going to arrange my 3 rocks in that respect, with the middle, the jogging one in the middle. All right, so I have no idea if you can see me right now, but I set this up earlier, so I think so. Okay, so I think when I'm walking, I'm going to drop it right about here. And when I'm jogging, about here. And maybe when I'm running, here. All right, so here we go. I'm going to start, this is my starting line. Okay, so I'm going to do walking first. All right, so I've got the hacky sack in my hand, just holding it. I'm not throwing it. And I'm going to walk. And I'm going to release right here. And okay, I hit the target, but, Yogi, I hit the target. However, not the bullseye, but that's okay. So we can say, yes, I hit the target. And we're going to measure from that rock where I released it to where the hacky sack landed. All right, so that was 47 centimeters. Yes. Okay. 1 meter, 47 centimeters. So, millimeters. So that's 0.47 meters. All right, so going back, wow, it's bright. Going back to our document here. So did I hit the target? Yes. And oh my God. Okay, let's see. So that was 0.47 of a meter, and it hit the target, yes. Oh, it doesn't want. All right, well, we'll just have it in there, I guess. Okay, all right, now we're going to go back, and hopefully we're seeing the target again. Can somebody let me know? Asher, can we see the target again?
Yes.
All right, thank you so much. Okay, all right, so now we're gonna jog. And now I wanna release right here at the middle rock. Okay, so I missed the target. So it rolled past the target. And I'm measuring from that rock where I released it. It's more than a meter. So that's 1 meter plus 40. So 1.4 meters, and I didn't hit the target. So screen. Whew, warm. Okay, so this was 1.4. 1.4 and no. And then we're going to do one more. Hopefully it's down there again. Is it, Asher? Can we see it again?
Yes.
Yeah, okay. All right, one last time. And I am going to go from the earliest rock, the one closest to the starting line, and I'm going to go faster. Well, I didn't hit the target. I almost did. I got closer than the last time. I don't know if you guys can see. All right, so we got to measure it. Last measurement. And this one's going to be pretty far. So that's here. All right, there's 1 meter. And it's a little more than the other one. Oops. 0.68. All right, 1.68. I'm going to get out of that sun. All right, 1.68, and it didn't quite hit the target. All right. 1.68 meters, and no. So messed that one up a little. That's a no. Okay. All right, so now we have our data, and let's take a look at, my low battery. All right, so, all right, we have what we need now, and now we just need to be able to write about it. So, pardon my my movement here, but my computer needed to come inside. Okay, so what do you think? So what was our accuracy like as we increased the speed? Did our accuracy improve or not improve? Who's got that? Look at our data table. Anyone? Okay. How about John? What you got?
Well, I noticed that every time when you walked, it was the closest. You jogged, it was not as close as you walked, but running was the farthest away.
Okay, so in other words, the faster I went, the less accurate I got.
Yeah.
Yes, I agree. Now, how do we know? And I left my phone outside, but I am going to write your name down. John, I'm still giving Dojo. Just don't have it right now. Okay, so yeah, that is right. And how did we know that? Like, if we look at our data, you'll see that, I'll be over it here. The only time I actually hit the target was when I was walking. And then I didn't hit the target during my jogging and running. But if you look at the distance from where I released to, you know, where it landed, do you see how the faster I went, the further the ball or hacky sack traveled once I released it? Would anyone like to, for some extra, several dojos, can anybody explain, according to Newton's laws, you can use, you know, first and second law here, but I'm really thinking more about inertia here. So the first law, can anyone explain why this is? Why the faster we were going, the further the hacky sack went? Can anyone explain that using inertia? Yes, Nate.
So I'm gonna go with the second law for a minute. According to like the second law, it's a formula: force equals mass times acceleration.
Yes.
And according to the first law, it says like an object in motion will stay in motion until it is acted upon a equal or unbalanced force. So when you were holding the ball, you were putting your force with it. I mean, you're both not the same object, but when you were running or jogging or walking, whatever, when you released the mass of when you were holding the mass of the ball, you increased the acceleration when you threw it. So that's just like second law. But with the first, when you threw it, an unbalanced force was acted upon by gravity and your throw.
Now, let me just interrupt just for a quick moment there. Remember, I didn't throw it though. All I did was release it. Now, if I did actually throw it, I would have been applying an extra force. But instead, all I did was just open my hand up and let it fall. So the unbalanced force then was only gravity. Once I released it, I was no longer acting on it. If I had thrown it, I would have been applying that extra force. And so then what would have happened if I had thrown it? Would it have gone further or less far, or?
It would have gone farther.
Yeah, exactly, because you would have applied more force, so it would have accelerated more and therefore covered more distance in the same amount of time. Yeah, okay. And somebody wanted to say something on chat. Let's see. Oh, maybe not. I don't see anything new. Okay, all right. So we did good today. We didn't didn't go as long, probably because of the video. Okay, so Nate was just explaining, and Nate, you're getting several dojo for that. Let's see, ×3. Yeah. So Nate was explaining how Newton's second law was explaining how it was accelerating more because there was a force acting on it, which was my body. So my force, remember, momentum is the force of a moving body, and I was delivering momentum because I was moving and I was holding on to the hacky sack. Now, according to Newton's first law, law of inertia, that hacky sack wants to keep on moving in the same direction that I'm going and in the same speed that I'm going. Why? Because it's with me, right? So why is it that we had to release it sooner when I was running? Think about Newton's first law and the object's motion when it was with me. Anybody want to explain it about inertia? How does inertia at play here that tells us we needed to release the hacky sack earlier before the target when we were going faster? Why? No, no one? Come on, guys. So, all right. So what does Newton's first law of inertia, say about an object in motion? Okay, an object in motion. Who can finish this? If you're in my homeroom, you had to do it for your homeroom question. So an object in motion, finish my sentence, someone. Bryson. Bryson.
An object in motion remains in motion until at a constant speed in a straight force until the net force acts on it.
Yes, right. At a constant speed, you meant to say instead of a constant force. But yes, right. So it's going to stay in motion, right? So the hacky sack that's with me is going my same speed and my same direction. And when I release it, it still wants to keep on going in that same direction and at the same speed as it was before. But it doesn't. It does for, a split second or two, but gradually there's an unbalanced force acting on it, and the unbalanced force is changing its direction. What is that unbalanced force that changed its direction? Instead of going in that straight line where I was going and at that same speed, it changed directions and went downward. Why?
Because of gravity.
Because of gravity, yes. Who said that? Going between chat box and, that must have been, I don't know. Who said it? Nobody wants to take credit for it for Dojo? Okay. All right. Oh, Nate. Okay, you're saying it in the chat. Okay, going back and forth between our chats and our videos here. Okay, so all right, so it was traveling at a particular speed, whatever my speed was, and in that direction. And when I released it, it wanted to continue doing that and did for, split second until the unbalanced force of gravity pulled it downward, changed its direction to downward, and accelerated towards the earth, because that's what gravity does. Is gravity always constant? Is it the same amount of force always? This is a trick question. So let me see.
Not really.
It's going to be our topic of discussion next Tuesday. We're going to talk about this next Tuesday. So, but you've learned about gravity. There's factors that make gravity change, right? It's not always constant. What makes gravity change, John?
Well, it depends on how big that object is and how much mass it has, and how big or how close it is to a bigger object.
Yes, exactly. So in the case of the hacky sack is being pulled to the earth. The earth is much, much larger than the hacky sack is. And if the hacky sack had more mass than it did, it would be pulled to the earth with a greater force than the hacky sack. If we used like a ping pong ball or something that had less mass, it would be pulled with less force, but it would still be pulled towards the ground and it would still fall. And so next week we'll talk about what happens when an object falls, and how, yes, gravity is unbalanced force pulling it down. Does anybody know what force might be acting against gravity in the opposite direction when something is falling? And there'd be more of it when we're outside. What do we have more of when we're outside? Maybe. Maybe you get this. Yeah, John?
Well, this is like a really big guess, but like the sun maybe because it's awesome. I don't know, but
We definitely do have more sun, especially today. But there's something else that is along those same lines. But what might work? Think about that ping pong ball for a minute. Try imagining throwing a ping pong ball outside. What's going to happen?
oh, I got it. The
Yeah.
wind.
Wind, yeah, air, exactly. Wind or air resistant. So when an object is falling, there is air acting around it, unless it happens to be falling in a vacuum, which is not real life. So there is some air resistance. And so next week we'll be talking about what happens when an object is falling. Gravity is pulling it down. Air resistance is like friction trying to keep it up. And eventually an object will reach a point where those forces are balanced if it falls long enough. And it will reach something that we call terminal velocity. So that's going to be our, on Tuesday of next week, we're going to look at that concept, and we're going to take some notes, our very last notes of the year. And then on Thursday, we're going to build our launching machines, our catapults, and then we will actually explore, objects falling and being launched, and we'll play a game. So that's kind of and that's the only thing that's left, really. So we've got notes on Tuesday. We'll build our machine on Thursday, and then we will have really one last week before our final week, and that's where we'll actually have a lab that we'll use our catapults for, and we will shoot marshmallows, but if you don't have marshmallows, we'll use other items. So got some fun things coming up, but just a few more classes. You guys are just looking at filling out this sheet. Like I said, it is supposed to be due on Friday, but I have given you a little padding on this, and it won't actually show up and be flagged as late until Monday at noon. So all you should need to do now is write your little paragraph, which we've talked about. You just need to put it in your own words. So remember, you are explaining how your speed affected where and when you had to drop the ball or the hacky sack to hit the target, and if your accuracy increased or decreased with the change in speed. So that part, you're looking at your data table, and maybe you have your own data, or maybe you're using this data. If you're using this data, if you're using this data, then it looks like our accuracy decreased the faster we got, or the faster I got. And I had to release the ball much further away from the target the faster I was going. So then, did your data support your hypothesis? Well, to answer that part of the question, you need to go back and look at your hypothesis. What did you say? Well, I believe that I said, and I don't know if you went with my version of this, but I said that I'd have to drop it before the target in order to hit the target. And the faster I move, the earlier I would have to drop it, and the less accurate I would be. And that is exactly what happened in my trials here. So in my case, my data did support the hypothesis. And then you need to also be able to explain how inertia, the first law, applies to this. So explain the motion of the hacky sack or your ball with respect to Newton's first law of inertia. And we did all of that together. So hopefully you have everything that you need to put this together and turn it in. Is there any questions that anybody has? Questions? No? Okay. Well, if you think of some, then you can come see me today in office hours from 2 to 3, or you can drop me a message in EdSpeak. And don't forget that your lab from Tuesday, the hula hoopla, is due tomorrow by noon. All right. I hope you guys have a great day, and I'll be around. So see you soon. Bye.